Students are requested to drop down their name for attendance purpose. We will be starting in a while. We'll be starting in a while. Meanwhile, you can drop down your names for attendance purpose. We'll be starting in a while. Okay, so let's start with the session now. See, we were on the methods of preparation for phosphine basically. So for laboratory method, if you see, when phosphine is pure, basically it is non-inflammable. That means it does not catches fire easily, but it becomes inflammable owing to the presence of P2H4 or P4 vapors. So if there are some impurities, some sort of impurities that are present basically in phosphine, such as P2H4 or P4, so it makes it inflammable, right? And as soon as the bubble of gas of phosphine comes in contact with the air, they catch fire spontaneously, right? And they form rings of smoke, which are known as basically what? Vortex rings. Okay. So if you basically treat P2H4 with oxygen, that is P2H4 is burnt in oxygen, you lead to the formation of metaphosphoric acid, which is given as HPO3. These common names you have to remember from the examination point of view, that HPO3 is known as metaphosphoric acid, right? So to purify basically phosphine from its impurities, what we do is we add potassium hydroxide, right, which yields pure phosphine, which yields or basically which removes impurities like phosphonium iodide from phosphine. Okay. Now next is the hydrolysis. So what is the basic phenomena of hydrolysis? Hydrolysis means that addition of water basically, right? So phosphine is prepared by the reaction of calcium phosphide with water. That means when you hydrolyze calcium phosphide with water or acid such as HCl, they get hydrolyzed and lead to the formation of phosphine. So this is the another method of preparation of phosphine. Next, coming on to the physical properties, if you see, phosphine is a covalent molecule. That means it is involving a covalent bonding. It has pyramidal structure like that of ammonia, and the bond angle here is 93 degree, right? That we have already discussed due to the Dragos rule. It is heavier than air and sparingly soluble in water, because water is a polar solvent basically, right? If you see here, and ionic compounds are more soluble in water than that of the covalent molecules. Therefore, it is sparingly soluble in water. It liquefies at minus 89 degrees Celsius and solidifies at minus 134 degrees Celsius. These things you don't have to remember. Basically, they are just the information about the phosphines, right? Now, next, if you see the chemical properties of phosphine, if you pass electric spark on phosphine, you will obtain phosphorus P4 plus hydrogen. Combustibility is, what is combustion? Basically, you burn the substance in the presence of oxygen, that is known as combustion. So if you burn phosphine in the presence of oxygen, that will lead to the formation of pentaoxide of phosphorus, that is P2O5 plus water, right? So the spontaneous inflammability of phosphine, as we have previously discussed, is due to the presence of P2H4, that is phosphorus dihydride, right? Phosphine itself is not inflammable, but it catches fire instantly due to the presence of some impurities such as P2H4 or P4 vapors. Next, leading to the chemical properties of phosphine, basically the chemical reactions of phosphine. If you see here, that when phosphine is absorbed on copper sulfate or basically mercury chloride solution, they lead to the formation of corresponding phosphides, right? Copper phosphide, mercury phosphide here, and H2SO4 and HCl are released as byproducts. So byproducts you don't need to remember. Basically, you can just remember that copper sulfate, when reacts with phosphine, it can form copper phosphide, or mercury chloride, when you treat it with phosphine, this can form corresponding mercury phosphide. Sorry. Coming on to the basic nature, because phosphines are basic in nature, as we have discussed, that we do go down the group, basicity increases, basicity of 15th group hydrides increases. So phosphine is more basic than that of the ammonia. So phosphine is weakly basic, and like ammonia, it gives phosphonium compounds. What is phosphonium? Basically, as NH4 plus is ammonium, similarly PH4 plus is phosphonium, right? So treating a base with acid will give you a salt, right? So here it is a base, you treat it with HCl, HB or HI, you will get the corresponding salts, that is the phosphonium salts. Here you are getting phosphonium chloride, phosphonium bromide, phosphonium iodide. This is a simple, this was a basic simple acid base reaction, right? Now coming on to the action of chlorine. So when phosphine burns in the atmosphere of fluorine, it leads to the formation of PCl5, that is phosphorus pentachloride. So this is how you can form PCl5. And when PH3 or phosphine reacts with nitric acid, it gives P2O5, that is the pentaoxide of phosphorus. Next, uses are important. Basically, the spontaneous combustion of phosphine, which was due to the presence of the impurities such as P2H4 or P4 vapors, basically is technically used in Holmes signal, right? So what are Holmes signals? Basically, there are containers containing calcium carbide. What is calcium carbide? CaC2, right? And calcium phosphide, Ca3P2, are pierced and thrown in the sea when the gas evolved are. So basically, when they are thrown in the sea, these containers, they evolve phosphine and ethine gas, right? That is CH triple bond CH, right? So due to the combustion, they form such colors, that is, you can see here, which acts as a signal basically, right? For the ships, they act as a signal, that is known as Holmes signal. And here also, basically military use the smoke screen to fool people around, right? So they are known as smoke screens. So phosphine is also a gas that is used in the smoke screens itself, which is used by the military people to fool around the enemies. Now next question is phosphine, the hydride of phosphorus. This we have already discussed, that it is covalent in nature. It is not metallic, it is not ionic, it is not non-metallic, rather it has a covalent bonding, and therefore it is a covalent compound. Next, this is now here, if you see that phosphonium iodide plus NaOH will form. So this will lead to the formation of phosphine. This will lead to the formation of phosphine. Now other hydrides, if you see ASH3 or SbH3, they are obtained by the hydrolysis of arsenide and antimonide. For example, here if you see that Zn3AS2, if you hydrolyze it with acid, basically HCl, it will give you what? Zinc chloride plus ASH3, and similar is for stilbene, Zn3 Sb2 HCl will give you what? ZnCl2 plus SbH3. So this is how the other hydrides of the group can be prepared. Now this is very important. If you see here that phosphorus forms pentahalides, but it does not form pentahydrides, right? pH 5 is not known. Why? Because if you see that in PCl5 the phosphorus has expanded its octet, right? So to exhibit pentavalency there should be a presence of an electronegative atom, because electronegative atom forces the electrons of the phosphorus to get excited. Okay, so here if you see that for example, xenon compounds are not much known, but still xenon OF4, xenon F2. Why? Because fluorine, oxygen are electronegative compounds, so they have much power to excite the electrons of xenon, right? And therefore they can form the compounds itself. Similarly, here also, as hydrogen is not sufficiently electronegative to make the d orbitals contract, so they could participate in the sp3d hybridization, because if you consider basically MH5, that is PH5 or NH5, if you say, they should be having trigonal bipyramidal geometry. What is trigonal bipyramidal geometry? 2 axial and 3 equatorial. This is known as the trigonal bipyramidal geometry, which is having a sp3d hybridization. So for that you need to excite electrons from p orbital to the d orbital, and the side atom should be electronegative enough, as hydrogen is not electronegative enough. So this hybridization is not possible in PH5, ASH5 or SbH5, right? So such a hybridization is only possible with electronegative elements such as chlorine, fluorine, oxygen. So therefore pentahalides are known, but pentahydrides are not known. This is an important question from the examination point of view. Now next we will discuss about the halides. We have discussed the hydrides. Now we will discuss about the halides. So there are two types of halides, basically trihalides and pentahalides. Trihalides and pentahalides, that is MH5 or EH5 base, MX5 where X is the halogen, or MX3 where M is the 15th element group and X is the halogen, right? X can be F also, chlorine also, bromine also, iodine also. So halides, if you see, all the elements of the group from trihalides of the type MX3, right, and except nitrogen all form pentahalides of the type MX5. That means that NX5 is not possible. Why it is not possible? Because of the absence of the d orbitals itself, right? While MX3 is possible for all 15th group elements, that is nitrogen, phosphorus, arsenic, antimony and bismuth, right? While MX5 is only possible for phosphorus, arsenic, antimony and bismuth, right? And X can be fluorine, chlorine, bromine or iodine. Now coming on to the study of trihalides, all trihalides are covalent except BiF3, which is ionic. Now this is very important. If you see here that bismuth is basically what? A metal, right? And fluorine is a non-metal, and we know that greater the electronegativity difference, greater is the ionic character. So here if you see that it is a pure metal while it is a most electronegative non-metal, right? So here the electronegativity difference between bismuth and fluorine is very high, therefore the compound is ionic itself, right? Rest of the trihalides are covalent. So like hydrides, these trihalides are also having the pyramidal structure, right? For example, if you see here that phosphine, we saw that it was having a pyramidal like structure. Similarly, PCl3 will also have a same structure. ASCl3 will also have a same structure with the hybridization of sp3, right? Now these trihalides can be easily hydrolyzed by water except NX3. Now this is very important, right? If you take, let us say, PCl3, ASCl3, SbCl3, BiCl3, they can be hydrolyzed, but why NCl3 or NF3 or basically NBr3, why they can't be hydrolyzed? This is due to the non-availability of the d orbital. What is the basis of hydrolysis? Basically what happens here is, when hydrolysis takes place, for example amongst nitrogen and chlorine, which is the most electronegative one. Okay, that we will discuss in the next slides. From the meanwhile, you can say that NCl3 if you see, NF3 if you see, or the trihalides of nitrogen if you see, what is happening here, that because there is an absence of d orbital, because of the absence of d orbital, they cannot be hydrolyzed, because for hydrolysis an empty orbital should be present. This is the important condition for hydrolysis, that hydrolysis of basically inorganic compounds, that an empty orbital should be present here, while phosphorus, arsenic, antimony and bismuth are having the vacant d orbital, so they can be easily hydrolyzed, right? Now second point about the hydrolysis is basically the oxidation state of the central element remains the same. Oxidation state remains the same, right? For example, here if you see, what should be the oxidation state of phosphorus in PCl3? Tell me, what is the oxidation state of phosphorus in PCl3? Anyone? What is the oxidation state of phosphorus in PCl3? You can comment down below and let me know. What is the oxidation state of phosphorus in PCl3? +3. Very good. So Sham, you have given the correct answer, that the oxidation state of phosphorus is +3 in PCl3, right? So here also if you will see, in H3PO3 it will also have a +3 oxidation state. In arsenic if you see, here the oxidation state is +3. Here also arsenic will have a +3 oxidation state. So after hydrolysis, the compound that is obtained will also have a same oxidation state. The oxidation state does not changes, right? And vice versa, if you say, see, on hydrolysis PCl3 gives H3PO3, or you can vice versa say that PCl3 is the anhydride of H3PO3. Okay, that we will do in the next one when we will study the oxides basically. So for the time being, you can remember that on hydrolysis, oxidation state does not change. Oxidation state does not change. This we have to remember. Okay. Now the trihalides of phosphor, and also one point that why NX3 cannot be hydrolyzed, due to the non-availability of the vacant orbitals, it cannot be hydrolyzed. Now the trihalides of phosphorus, arsenic, antimony act as Lewis acid and combine with Lewis bases, right? So trihalides of phosphorus if you see, PCl3, PF3, arsenic if you see, or antimony if you see, they all act as Lewis acids, right? They are electron deficient, basically they act as Lewis acid and they combine with Lewis bases. So here you can see that PF3 on combination with F2 will give you PF5, SbF3 on combination with 2-fluoride will give you SbF2 negative, right? So these here basically are acting as what? The Lewis acids. Question is, which of the following is not hydrolyzed? We have already learned that NX3 cannot be hydrolyzed due to the non-availability of the vacant orbital. So option is D here. Now, nitrogen trihalides have least ease of hydrolysis. Now here if you see that ease of hydrolysis, bismuth Cl3, SbCl3, AsCl3, PCl3 and then NCl3, it cannot be hydrolyzed basically. So ease of hydrolysis increases down the group. Ease of hydrolysis increases down the group. So what is happening here, if you see that bismuth is electropositive, right? Because the if you see here, the partial positive character that will be on bismuth is very much high. So it tends to attract the negative dipole of the water. Negative dipole of the water is much more attracted towards it. Therefore, it is easily hydrolyzed than that of the others, right? Because the electropositivity of the central atom, that is the from phosphorus to bismuth, it increases and therefore it tends to attract the negative dipole of the water molecule itself and therefore it is easily hydrolyzed. So NF3, if you see, it is a colorless gas, odorless gas, and the most stable of this series, and it has the lowest reactivity. NCl3, if you see, it is a yellow oily liquid that reacts with water to form ammonia and hypochlorous acid. So hypochlorous acid and other acids of chlorine we will learn in the halogen family. Ni3 is shock sensitive and decomposes explosively when touched. Now this is very important. Why dipole moment in ammonia is more than that of NF3 molecule, even though NF bond dipole moment is higher than that of the NH bond dipole moment. Obviously, if you consider nitrogen and fluorine and nitrogen and hydrogen, fluorine is very much electronegative at that compared to nitrogen. And here if you see, the electronegativity of nitrogen is greater than that of hydrogen. Here if you see, electronegativity of fluorine is greater than that of nitrogen. So if you draw these structures, basically this is the structure for NF3, right? The dipole will be towards the fluorine itself. So the resultant dipole will be here. While for the lone pair, if you see, the dipole will be here. So basically these dipoles cancels out each other, not equally, but to some extent they cancel out each other. Therefore, the resultant dipole moment of the NF3 molecules is less than that of the NH3 molecule. So here if you see NH3, the resultant dipole is added because here nitrogen is more electronegative than hydrogen. So the resultant dipole will be added basically. The two resultant dipoles will be added, where here they will be cancelling out each other, right? So therefore NF3 molecule is having less dipole moment as that compared to the NH3 molecule. Now coming on to the phosphorus trichloride. So it is obtained by passing dry chlorine over heated white phosphorus. That means if you heat white phosphorus with dry chlorine, you will get PCl3 here, right? And also if you take white phosphorus and react it with thionyl chloride, which is known as basically the chlorinating agent. You will learn in organic chemistry that it is known as the chlorinating agent, right? So P4 on reaction with thionyl chloride, it can also give PCl3. This is how phosphorus trichloride can be formed, right? So it is having a pyramidal shape. We have already done this, in which the hybridization of phosphorus is sp3. Phosphorus trichloride, if you see, it is a colorless oily liquid and hydrolyzes in the presence of moisture itself, right? So PCl3, if you see, it hydrolyzes to H3PO3, that is metaphosphoric acid, and it also reacts with alcohol containing group. For example, if you see CH3COH, it will react with acid containing group or alcohol containing group, that is C2H5OH, and acts as a chlorinating agent, right? Here if you see, acylation is taking place, CH3COCl is being formed, right? And here if you see, that OH group is replaced by chlorine itself. Here also C double bond OH, this OH is replaced by chlorine itself. So PCl3 is also known as the chlorinating agent. So PCl3 hydrolyzed in the presence of even atmospheric moisture gives fumes of HCl. This is very important. If you keep PCl3 in the atmosphere itself, it can get hydrolyzed even with the moisture that is present in the atmosphere. Now coming on to the pentahalides. So pentahalides, we have seen that the hybridization is sp3d, trigonal bipyramidal, and in trihalides it was sp3, that is tetrahedral. And pentahalides, if you see, there are 5 covalent bonds that are being formed. Now this is important, that pentahalides have less thermal stability as compared to that of the trihalides. That means pentahalides decompose on heating. Pentahalides, if you see, are more covalent than that of the trihalides. Why? Because if you see, in PCl5 let us take and PCl3 let us take, this is +3 and this is +5, and we already, to Fajan's rules, we have studied that that phosphorus, or the central atom basically, which is forming a cation, the cation should be, the greater the charge on the cation, more is the covalent character, right? So here if you see, that phosphorus is having a +5 charge, and here if you see, phosphorus is having a +3 charge, right? So therefore the PCl5, according to Fajan's rule, will have a covalent character than that of the PCl3. Now all pentahalides also act as Lewis acids. Trihalides were also acting as Lewis acids, pentahalides will also act as Lewis acids. So here if you see PCl5 plus Cl negative, it is giving PCl6 negative, so here it is acting as a Lewis acid. Similarly, if you see SbCl3 plus Cl negative, it is forming SbCl4 negative, so here also SbCl3 is acting at what? A Lewis acid. Now this is very important. PCl5 is very important from the examination point of view. So in gaseous and liquid phases, it exists as a trigonal bipyramidal structure only in gaseous and liquid phase, right? So here if you see the trigonal bipyramidal structure, if you see that axial bond lengths are different from the equatorial bond lengths, right? Axial bond lengths, axial PCl bonds are longer than that of the equatorial PCl bonds. Why this is happening? Because see here that sp3d hybridization is taking place and the d orbital that is involved here is basically dz square, right? So if you draw dz square here, let us say here, right, this is dz square, basically positive lobe here, positive lobe here and a negative ring here, right? So the ligands, that is the chlorides, right, the Cl negative is coming from the z axis only, z axis, along the axis, right? So therefore this orbital is suffering more repulsion, dz square is suffering more repulsion, and therefore the ligands that are present at the axial position, if you see the Cl position, let us mark it Cl1 and Cl2, right? So Cl1 and Cl2, when they will be coming, they will be facing more repulsion, and therefore due to the electronic repulsion, the axial bond lengths are more as compared to that of the equatorial bond lengths. Okay. Now phosphorus pentachloride, if you see in the solid state, it exists as an ionic solid. This is also very important. It exists as PCl4 plus and PCl6 negative. So here if you see, if you draw the structure of PCl4, it is tetrahedral, and if you draw the structure of PCl6 negative, it is octahedral in nature. So this is the basic structure of PCl4 negative, that is tetrahedron, and this is octahedral. So this is very important, that in gaseous and liquid state it was present in trigonal bipyramidal geometry, but in solid state it is present as an ionic solid, that is PCl4 negative, PCl4 positive and PCl6 negative. This is the cation and this one is the anion, right? So PCl4 positive will be having a tetrahedral geometry, while this other one will be having a octahedral geometry. Now here if you see that preparation of phosphorus pentachloride can be done by white phosphorus. If you treat it with chlorine, you can get PCl5, and also if you treat it with thionyl chlorides, SO2Cl2, basically you can also obtain PCl5. The PCl5 in appearance, it is a yellow whitish powder and it is very moist in air. That means it hydrolyzes readily, right? So PCl5, when it hydrolyzes, it forms POCl3. Right, and POCl3 on further hydrolysis gives H3PO4. H3PO4. So you have to, basically the question can arise here that what are the products of hydrolysis of PCl5 and what are the products of hydrolysis of PCl3. So you must be remembering these two equations. So when heated, PCl5 sublimes, but when you strongly heat it, it decomposes into PCl3 plus chlorine, because the pentahalides are having lesser thermal stability as that of compared to the trihalides itself, right? And on reaction with the organic compounds like that of PCl3, it also acts as a chlorinating agent. So if you treat ethanol with PCl5, you can get ethyl chloride. If you treat acetic acid with PCl5, you can get CH3COCl. Right, and the byproducts that will be formed here are POCl3. So these two reactions are very important. You will learn it in the alcohol chapter also, I guess, or the haloalkanes chapter in organic chemistry. Finely divided metals on heating with PCl5 give corresponding chlorides. Now this is very important, that if you take silver or tin basically and heat it with PCl5, they will lead to the formation of silver chloride and tin chloride respectively. Now the question here is, are all the 5 bonds of PCl5 equivalent? That we have already studied, that axial bonds faces more electronic repulsion, and therefore whenever you will draw the structure of PCl5, the axial bond lengths will be greater than that of the equatorial bond lengths, because they are suffering more electronic repulsion. So axial bond lengths are more than that of the equatorial bond lengths, and therefore all 5 bonds of PCl5 are not equivalent. Now coming on to the oxides of group 15, this is also very important. So here if you see The elements of group 15 combines with oxygen directly or indirectly to form basically different types of oxides, right? So if you take nitrogen, it is forming oxide in +4 also, +3 also, +5 also, +2 also, +1 also, right? So in basic basic inference that you can make from this table is the oxidation state of group 15 element in different oxides. For example, in N2O5, nitrogen will have a +5 oxidation state. For N2O4, it will have a +4 oxidation state. For N2O3, it will have a +3 oxidation state. So this you need to remember, or there is no need to remember. Basically, you can see here also, right? N and oxygen. So basically oxygen is having 2 here, and if the formula is N2O5 basically, so 2 will go here. That means the oxidation state of nitrogen will be what? +5. Therefore, it is going here. So this will be N2O5. Right. Now, phosphorus, if you see, it is forming oxide in +5, +4 and +3, while it is not forming any of the oxide in +2 and +1 oxidation states. So the common oxides of phosphorus are P4O10, P4O8, P4O6. Right. And for arsenic, antimony and bismuth, you can see that only +5 and +3 oxidation states are more frequent in the case of oxides of these elements, right? So for the time being, you need to remember the nitrogen and phosphorus oxides very efficiently, and structures are very important from the examination point of view. Structures of oxides of nitrogen and phosphorus are very important from the examination point of view, that we will discuss in the session itself. Pay attention to that structures. Practice these structures basically more than 2 to 3 times, so that you don't make any mistake while writing down the structures, because questions from structures are very common in the competitive exams as well as your boards exam also. Coming on to the oxides, so all the oxides of nitrogen and phosphorus are strongly acidic in nature. Now this is very important, as we are studying that basically group 15 elements, if you say, they are non-metallic in nature. They are non-metallic in nature except bismuth, that is pure metal, right? So generally p block elements are non-metals, but the lower members are the metal itself. So if we talk about nitrogen and phosphorus only, so they are non-metals, and the oxides of non-metals are what? Basically acidic in nature, right? But here if you see NO and N2O, these are neutral. These are neutral oxides of nitrogen. So oxides of arsenic, if you take, they are weakly acid. Oxides of antimony, if you take, they are amphoteric. And oxides of bismuth, if you take, they are weakly basic. Why? Because if you see that electropositivity of, if you say that metallic character increases down the group, and we know that the oxides of metals are what? Basically basic in nature, right? So if you move down the group, the oxide will move towards the basic nature more. So nitrogen and phosphorus, if you see, they will be having acidic oxides. Arsenic and antimony, if you see, they are having amphoteric oxides, and bismuth, if you see, it is having basically a weakly basic oxide, because the metallic character is increasing down the group. You can remember it that way. Now oxide of nitrogen, if you see, N2O5, N2O4, N2O3, they are strongly acidic, while NO and N2O are neutral. Now this was a common question in the JEE or NEET, I guess. It was asked in the exam that which of the following oxides are neutral. So this you need to remember, that which of the following oxides are neutral of nitrogen, that is NO and N2O. Oxides of phosphorus, if you see, it is P2O5 or P2O3, right? Oxides of arsenic, if you see, that we have already done As2O5 or As2O3. Similarly for antimony also, and for bismuth also, this we have done, that the upper two are the acidic, then amphoteric, and then basic. Now, nitrogen could exhibit larger number of oxidation state. This we have already discussed. +5, +4, +3, +2, +1 are the oxidation state that are exhibited by nitrogen in itself, and this is due to the possibility of p-pi bonds, right? Nitrogen can form p-pi multiple bonds with oxygen. That means a double bond. So p orbital will be used here, p orbital will be used here, therefore it is known as a p-pi bond. But the other atoms of group 15, for example phosphorus, arsenic, antimony, bismuth, they are too large, right? So effective overlapping is not taking place in these elements. So their 4, the p pi bonding, if you see, or the d pi bonding is not as much strong as that of the p pi bonding of nitrogen and oxygen here, due to the poor overlap between the orbitals. Right. Now, some of the oxides of nitrogen, example NO, if you see, it is a odd electron species. This is also very important, that which oxide of nitrogen is a odd electron species. NO is basically what? A radical, right? It is a odd electron species, so they are definitely paramagnetic. Obviously, if they are having odd electron, let us say, for example, let us take element X, let us say, and it is having a odd electron. That means, let us say that it is having a 7 electron, right? So 1, 2, 3, 4, 5, 6, 7. So these are paired, but one electron is left unpaired. So wherever there is a odd electron species, it will be definitely paramagnetic in nature due to the presence of the unpaired electron itself. Now, next coming on to the common methods of preparation basically. So N2O is basically known as nitrogen oxide or dinitrogen oxide, and the oxidation state of nitrogen here is +1. If you decompose ammonium nitrate, you will get N2O plus H2O. Right, this is the basic common method of preparation of dinitrogen oxide, and the physical appearance and chemical nature is it is a colorless gas basically, and it is neutral in nature. That we have already done, that N2O and NO are neutral in nature. Similarly, nitrogen monoxide oxidation state of nitrogen is +2, and the common method is NaNO2 plus FeSO4 plus H2SO4 will give you what? The formation of NO. So this is also a colorless gas and it is neutral. Now next you come on to N2O3, that is known as dinitrogen trioxide. Here the oxidation state of nitrogen is +3. So if you combine NO and N2O4, you can get N2O3, which is a blue solid. This is important. Others are gases and this is a blue solid, and it is acidic in nature. Now coming on to the NO2, this is very important. This you will learn in the detection of anions and cations also basically. So nitrogen dioxide, that is the NO2, is a brown gas and it is acidic in nature, right? So it can be formed by the decomposition of lead nitrate, giving NO2 plus lead oxide. Similarly, others also, if you see N2O4, that is dinitrogen tetraoxide and pentaoxide, if you see. So dinitrogen tetraoxide can be formed by the dimerization of NO2. So if you cool NO2 basically, you will get N2O4, and it is also a colorless solid. It is liquid in nature. It can be a liquid also and it can be a solid also basically, and in both forms it is colorless only, and it is acidic in nature, right? Here if you consider N2O5, so it is a colorless solid and it is acidic in nature, which is formed by the reaction of nitric acid with P4O10 giving HPO3 plus N2O5. So these methods of preparation you don't have to remember. The main point that you have to remember in this particular table is, first, that N2O3 is a blue solid and it is acidic in nature. Second one, that the color of NO2 is a brown gas, right? And the third one, that N2O4 can be formed by the dimerization of NO2. This much you need to remember from this particular table, and also the oxidation state of nitrogen in various oxides. Now coming on to the structures, these are very important. These are very important. The structures are very important, whether it be of nitrogen oxides or the phosphorus oxides. So N2O, if you draw, there is a double bond between nitrogen and nitrogen and nitrogen and oxygen, and if you draw the resonating structure, basically this bond will shift into this side, so this will be N triple bond NO, right? So this is the basic structure of N2O. Now if you consider the structure of NO, which is basically an odd electron species, can you see here? 2 electrons here, okay, 2 electrons here, okay, 2 electrons here, okay, but here if you see, there is a single electron here, so basically it is an odd electron species, right? N2O3, if you see, there is a single bond between nitrogen and nitrogen, double bond O on each nitrogen, and a single bond here with a oxygen, right? So you can draw the resonating structures of N2O3 also. Again, I am repeating that you need to practice these structures again and again. Practice them because they are very important from the examination point of view. In P block, structures will definitely be the target of the examiner. Now NO2, if you see, nitrogen, a single bond with oxygen and a double bond with oxygen, right? Or you can draw the double bond here and a single bond here basically the resonating structures. N2O4, if you see, nitrogen and nitrogen, if you see a single bond here, oxygen and oxygen with a single bond here, and double bond O on the both the nitrogens, right? So NO2, if you see, it contains odd number of valence electron. Can you see here? One electron here, one electron here. It contains odd number of valence electron. So basically NO2 dimerizes to N2O4 that we have already discussed on cooling, so as to become even number of electrons. We have done in chemical kinetics also that ionic reactions and radical reactions are very fast. Why radical reactions are very fast? Because they are very unstable. They are odd electron species and they are very unstable. So NO2 in itself is very unstable, therefore it dimerizes to form even electron species, that is N2O4. Now next is the N2O5. So the difference between the N2O4 and N2O5 is that you just need to insert a oxygen in between for N2O5. Can you see the difference here? N2O5. What is the covalence of nitrogen in N2O5? Can anyone answer? What is the covalence of nitrogen in N2O5? What is the covalency of nitrogen in N2O5? Look at the structure and tell me. Look at the structure and tell me what is the covalency of nitrogen in N2O5. Anyone? Anyone with the answer? What is the covalency of nitrogen in the structure of N2O5? This is the structure of N2O5. Anyone with the answer? Okay, first you tell me what are the number of electrons for nitrogen here. What are the number of electrons for nitrogen here? Is it more than the octet, or is it less than the octet, or is it exactly 8 electrons? This is a part of chemical bonding only, you should know this. We have done chemical bonding in 11th class itself. I am waiting for your answers. At least tell me that how many electrons are present for nitrogen here. Is it 8, more than 8, or less than 8? Shraddha, Tara, Arvind, Sham. Okay, so if the electrons, the number of electrons for nitrogen is 8, Sham, then what is the covalency of nitrogen here? What is the covalency of nitrogen here then? Anyone? Manish, Shrivasthan, Pavan, Shivani, Lakshmi. See here, nitrogen, if you consider, it is having 5 electrons of its own. right? 6, 7 it is taking from nitrogen, oh sorry, oxygen. So 2 from here, 1 from here, let us say, right? So 8 electrons. Now this bond is particularly a dative bond because nitrogen cannot expand its octet. It cannot have more than 8 electrons. So this particular bond will be what? A dative bond here. Similarly for this nitrogen also, this particular bond will be a dative bond because octet is already complete, right? 1 electron it is taking from oxygen here, right, and 2 electrons it is sharing with this oxygen here because of the presence of double bond. So 5 plus 3 will give you 8, and about this oxygen if you see, it will make a dative bond or a coordinate bond basically, right, in which it is not sharing the electrons of oxygen, rather it is a covalent bond. What is a coordinate bond? Basically it is a covalent bond in which only sharing of electrons is there, but only from one species only, right? So here oxygen is not sharing any of its electron, rather nitrogen is giving its electron, sharing its electron, not giving its electron, rather sharing its electron. Okay, so a dative bond is present here. Now you calculate the covalency here, it will be equal to 4. It will be equal to 4. 1, 2, 3, 4. So the valency of N2O5 in dinitrogen pentoxide is 4. Because 3 are the covalent bond and 1 is the coordinate covalent bond. This one is the coordinate covalent bond, and these 3 if you see, 1 sigma bond, 1 pi bond, this 1 sigma bond, and this is 1 dative bond. So 1, 2, 3 and this one is 4th one, right, which is forming a dative bond. So the covalency here is 4. Which of the following oxides is the most acidic? Which of the following oxides is the most acidic? Anyone with the answer? So here if you see, we have already seen that basic characters increases down the group. So the most acidic oxide will be N2O5 here. Now coming on to the preparation of oxides of nitrogen, N2O is also known as laughing gas. It is also known as laughing gas, right? So preparation can be done by NO plus H2O plus iron will give you what? N2O. Berthelot's method, if you say ammonium nitrate, this is important and common method. So this you need to remember that ammonium nitrate on decomposition or basically on heating will give you N2O plus H2O. Similarly, NaNO3 plus ammonium sulfate will give you N2O. Right, properties we have already done. It is colorless, fairly unreactive, pleasing odor, sweet taste. It supports combustion and it is a neutral oxide. This is very important that it is a neutral oxide. Next, if you come on to the nitric oxide, the common method of preparation is NaNO2 plus FeSO4 plus H2SO4 will give you what? NO, nitric oxide. Or commercial method if you say N2 plus O2, simply combining, or you can term it as a combination reaction. So N2 plus O2 will give you 2NO. Lab method is you treat copper with nitric acid, you will get copper nitrate plus H2O plus NO here. Similarly, if you treat ammonia plus oxygen, if you combust ammonia basically on the platinum surface and treat it with oxygen, this is known as the Oswald process, you will get the NO formed. Properties, it is colorless, paramagnetic, that we have already done. It is a slightly toxic gas and it is blue in liquid state and it is also neutral in nature. So, if you treat FeSO4, that is the ferrous sulfate solution, with NO, a dark brown color is formed, that is FeSO4.NO. Now when you heat it, you can get the FeSO4 and pure gas of NO you can get. So this is how basically you can remove the impurity from the NO gas, right? Or you can treat this particular complex of iron with NO, you will get a hydrated nitrosyl complex, again heat it. This is also used to purify the NO gas, right? So NO, if you treat it with oxygen, it will give you NO2. This is also important reaction. NO plus O2 will give you NO2, which is brown in color. I have already told you that this is important, that NO2 is having a brown color. So if you see here that NO can act as a reducing agent also and as a oxidizing agent also. This is the special property of NO. Coming on to NO2, that is the nitrogen dioxide. So NO plus O2 will give you NO2. This we have already done, or you can just decompose lead nitrate, that will also lead to the formation of nitrogen dioxide, or you can treat copper with nitric acid, which will lead to the formation of copper nitrate and NO2. Coming on to the properties, it is a highly toxic paramagnetic reddish brown gas. This is important, that NO2 is a reddish brown gas. I am repeating it again and again because it will be beneficial in the cation and anion detection itself, right? It is having a choking odor and it is also acidic in nature. Reactions, if you see that NO2 on reaction with water will give you HNO2 plus HNO3. So basically if you see here that it is a mixed anhydride of HNO2 and HNO3. Why it is called an anhydride? Basically because NO2 on hydrolysis is giving HNO2 and HNO3. That means if you remove water from HNO2 and HNO3, that means you unhydrate it, it will be forming NO2. So NO2 vice versa is the anhydride of mixture of HNO2 and HNO3. If you cool basically NO2, you will get what? N2O4, which is a colorless solid or liquid, and it is also acidic in nature, right? NO2, if you treat it with the photochemical decomposition, basically it will lead to the formation of NO and O. It is combustible and supports the combustion of burning phosphorus, magnesium or charcoal. Burning sulfur or candle is extinguished. Now next, fifth one is that it is oxidizing and reducing in nature. So all you need to remember for this oxide of nitrogen is that first this point, this reaction is important, that NO2 converts into N2O4. This reaction is important, that NO2 on photochemical decomposition will yield you NO plus oxygen atom. And you need to remember that basically HNO2 and HNO3, if you anhydrate it, that will lead to the formation of NO2. Basically NO2 is the anhydride of the mixture of HNO2 and HNO3. So here if you see N2O3, that is known as the nitrogen sesquioxide. Its common name is nitrogen sesquioxide. So if you treat NO with N2O4 at 253 Kelvin, this leads to the preparation of nitrogen sesquioxide, right? It is blue in solid form, and it is also acidic in nature, right? So N2O3, if you hydrolyze it, it is giving HNO2. That means what? That N2O3 is the anhydride of HNO2. Now you can compare the oxidation state. Basically oxidation state of nitrogen is what? +3 here. Oxidation state of nitrogen here also is +3. So that means that on hydrolysis the oxidation state of the central atom does not change. Absorbed by sulfuric acid. So if you treat N2O3 with H2SO4, you will get a nitroso-sulfuric acid complex and water is released. So in this particular slide, this reaction is very important. Basically the hydrolysis part. Now coming on to N2O5, that is the dinitrogen pentaoxide if you see. So HNO3 on reaction with P2O5 will give you N2O5. This is the common method for preparation. AgNO3, silver nitrate on reaction with chlorine will give you AgCl and N2O5. Similarly, N2O4 on reaction with ozone will give you N2O5, right? So its properties is that it is a crystalline solid and basically it's sublime. Sublimes is basically what? That converting solids, solid into gas without passing into the liquid state, or converting gas into solid without passing into the liquid state. N2O5, if you treat it with water, it get hydrolyzed into HNO3. That means N2O5 is the anhydride of nitric acid. If you treat N2O5, because it is acidic in nature, it reacts with a base and leads to the formation of NaNO3. Similarly, if you react it with peroxide, it will lead to the formation of pernitric acid. Formula you have to remember that pernitric acid, the formula is HNO4. Coming on to the structure of N2O5, we have already discussed that here is a dative bond basically. So it is having a ionic structure in solid form. So in solid form it will be NO2 plus and NO3 minus. Therefore it is also called nitronium nitrate, because this ion is called nitronium, this ion is called nitrate. The reddish brown colored gas. See, I already told you the reddish brown colored gas is which one? Basically NO2, right? The only oxide of nitrogen which is reddish brownish color in NO2 is formed when nitric oxide is oxidized by the air. So by the color also you can by seeing the hint also here that it is reddish brown colored gas, you can just identify the option, the correct option. Why on cooling NO2 loses its paramagnetic nature? This also we have done, that NO2 basically on cooling it dimerizes into N2O4 to remove its paramagnetic nature. Now it becomes what? Diamagnetic, as it was a odd electron species. Now it is paired in N2O4. Right. Now next we will do the phosphorus oxides, that is P2O3 or P4O6 basically. Just a second. See, for nitrogen and phosphorus oxides, if you see, the oxides structures are very important, right? Whether it be oxides, whether it be halides, structures are very important from the examination point of view. So, the preparation of P2O3 or P4O6, that is phosphorus trioxide, is when you heat white phosphorus with a limited amount of oxygen, right? So, it is a white solid wax, garlic odor and highly poisonous. So, this structure you need to remember. This structure you need to remember. How will you draw it? Draw the chair conformation of cyclohexane basically. Right. Now place phosphorus, oxygen. There is no PP bond. There is no PP bond in the oxides. This you have to remember. The phosphorus and phosphorus will be separated by oxygen itself everywhere. So this will be this oxygen, phosphorus, oxygen, then here phosphorus, then again you will connect it with oxygen, this you will connect it with oxygen. So this is the basic structure of what? P4O6. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So 4 phosphorus and 6 oxygen. Next, coming on to P2O5 or P4O10. So if you treat white phosphorus with excess oxygen, if you treat it with limited oxygen, it will lead to the formation of P2O6. Now here if you see, sorry, P4O6. Here if you see that white phosphorus when heating it with excess amount of oxygen, that will lead to the formation of P4O10. So it is also a garlic odor substance, white crystalline solid, and it also sublimes, right? Now this is very important, that P4O10 on reaction with cold water it yields metaphosphoric acid, on reaction with hot water it leads to the formation of orthophosphoric acid. This is very important. This will be covered in the oxoacid part, structures of metaphosphoric acid and orthophosphoric acid, and the basically nomenclature of metaphosphoric, orthophosphoric, phosphoric acid, that will be covered in the oxoacids part, right? And uses P4O10 is a, or P2O5 is a dehydrating agent. That means it removes excess water, or it anhydrates a substance. It removes water from the particular compound. Now the structure is very important. Once you learn the structure of the previous one, you just have to put the double bond O here. With each phosphorus you have to add double bond O. So this was what? Basically P4O6. It was P4O6. Now on each phosphorus you will be adding double bond O. So 1, 2, 3, 4 oxygens are added. So this will become what? P4O10. P4O10. So this is the basic structure of P4O10. What is the number of POP bonds in P4O10? So here if you draw these structures of P4O10, POP bond is 1 bond, 2 bond, 3 bond, 4 bond, 5 bond and 6 bonds. So how many POP bonds are there? 6 bonds. So such type of questions are asked from these structures, or rather they will ask you that what are the number of P double bond O present in P4O10. So that you also have to tell that what are the number of P double bond O present? 1, 2, 3, 4. So 4 P double bond O are present in the P4O10 structure. So these variety of questions are asked from the structure itself. Oxides of other elements, if you see, arsenic forms As4O6 or As4O10, antimony forms Sb4O6 or Sb4O10, while bismuth forms only Bi2O3. This is due to the inert pair effect. This is due to the inert pair effect, that it is stable in the lower oxidation state, that we have already discussed, that the heavier member of the groups are stable in the lower oxidation state. Basicity of oxides or hydroxides, if you see, they will increase down the group. That we have already done due to the increase in the metallic nature. So already we know that metallic oxides are basic in nature, therefore the metallic character or the basicity of oxides increases down the group. Stability of pentoxide decreases on down the group because bismuth does not form pentoxide. This we have also done, that it does not form. Why does it not form pentoxide? Basically because it is more stable in the lower oxidation state. Pentoxides are more acidic than that of trioxide. This also you can explain on the basis of covalent character, as pentoxides are more covalent than that of the trioxides, therefore they are more acidic than that of the trioxides. The more covalent, the more acidic. So that's all for today. In the next session, we will be discussing, I guess, oxo acids. The structure of oxo acids are also very important. So in today's lecture, the structures are very important from the examination point of view. So practice these structures itself, right? And keep on reading your NCERT part wise, so that you will not get a burden in the end that you have to do the whole P block, you have to mug up the whole P block, then you will end up watching the sessions again and again, and your mind will be tired of mugging up all the things, right? So rather mugging up it in one go, just divide them into parts as we are doing, right? See first session, revise that from the NCERT, see the second session, revise that from the NCERT, see the third session, revise it from the NCERT. So this is how you can peacefully do the P block chapter itself. Okay, so that's all for today. Thank you.